Brad, I guess like the public
So
section.
if you get longer, I'm sure actually Brad will be here or others will be here, then they can catch up with you.
Okay. Yeah. However you'd like to do it.
Yeah, but I think we'll have time for the public comments or questions, so that's always ideal, but we can always push those back if we had to. We've had to do that before. All right, so then let's get started. So this is the defense for Shruthi Suresh. She got her master's here, also in Purdue, under me. And so a lot of this work really extends from that, which was focused on, we kind of did it backwards, from humans into rodents. But the rodents give us a lot of more information, controlled studies, and she'll talk about that. And I said, why do you need to graduate so soon? She has a fellowship till in this May with the Bildwin. And she said, I'll do whatever it takes so I don't have to bring food and coffee to the, to the defense. So, yeah. So I remember when I did my defense, I had one committee member who just moved to Texas. And so he was on speakerphone, and that was such a huge, big deal, having someone that was not physically there. Now here we are, and we're all in different places. Anyway, Shruthi, she's got tons of awards, and I think you're familiar with all that, and she's done great things, both in research and teaching and doing practical things with epics. And so now this is really just doing great work, and I'll let her introduce the topic.
Cool. Awesome. Thanks so much, Brad. Okay, so let's just go ahead and get started. Like Brad said, a lot of my work that I'll be presenting today is primarily rodent-based, but I'll also touch a little bit upon what we've worked on in the past and kind of go over all of the different aspects of the topic itself. So we'll probably do the presentation first, and then we'll have the Q&A section afterwards, most likely. So yeah, like Brad said, my name is Shruthi, and all of you that are here hopefully know that. And so what I'll be presenting today is the detection of dysautonomia in spinal cord injury through non-invasive sensing techniques and multi-modal sensing and machine learning, essentially. So we'll just jump right in. The autonomic nervous system is, as the name suggests, an autonomous system which controls various involuntary reactions, such as the beating of the heart, digestion, functioning of other vital organs that we hardly think about. So it comprises two main aspects of the system itself, which are the parasympathetic nervous system, or the vagal system, and the sympathetic nervous system. The sympathetic nervous system actually activates the fight or flight response, which causes telltale signs of sweating, increase in heart rate, narrowing of vision, all of which I'm experiencing right now. And the vagal system activates the rest and digest system, returning the body back to a state of calm. So these two systems complement each other and allow our bodies to maintain proper function and balance to make sure that there isn't some sort of dysfunctional aspect of it. However, in some cases, the autonomic nervous system doesn't necessarily perform as well as it does in individuals who do not have some form of disability. So this could be either due to hyperactivity of one of the two branches of the autonomic nervous system, so either the sympathetic or the vagal. So this dysfunction is known as dysautonomia, and dysautonomia affects approximately 70 million people worldwide. It can present itself as cardiovascular difficulties, gastrointestinal issues, and pseudomotor complications, which means that sometimes there is a sweat disorder, which means that a person is either sweating too much or maybe not sweating enough. It often occurs in individuals with stroke, spinal cord injury, Parkinson's disease, or even diabetes. In this study specifically, I will be focusing on dysautonomia after spinal cord injury, more particularly on a very specific sort of dysfunction known as autonomic dysreflexia. Now, those of you in the audience have heard me speak about this several times, but I'll go over it one more time. Autonomic dysreflexia is a dysfunction of the sympathetic nervous system, which occurs in individuals with spinal cord injuries above the T6 level. So this is often triggered by various stimuli below the level of injury, such as restrictive clothing or something more severe like a urinary tract infection, which can take several days to clear out. So essentially what it leads to is the sympathetic hyperactivity occurs as a result of one of these stimuli, and it causes a massive increase in systolic blood pressure, leading to severe hypertension. This hypertension in results causes a cascade of events which lead to a lot of symptomatic presentation above the level of injury. So you have sweating, you have flushed faces, a pounding headache, which may not go for several days. And the issue, honestly, is that individuals experience different types of symptoms, and it could be because of different triggers. So they often have to learn to identify what their triggers are and what their symptoms could be. And it's very important for them to manage these symptoms because poor management often leads to hemorrhaging, strokes, and in a worst case scenario, it can cause death. So currently, knowing one's own symptoms and triggers is the best way that is recommended by almost all clinicians after a spinal cord injury. However, this can be problematic just because often AD will present itself 2 to 5 months after a spinal cord injury, most commonly. But it only takes about a month of in-hospital rehabilitation for individuals with spinal cord injury. So they might not even have enough time to experience the various symptoms and triggers while they're in hospital and while they're under clinical care. So basically, it tends to cause a lot of difficulties for individuals who are newly injured, especially because of the lack of familiarity with it. The second is the AD wallet card. So as you can see here, it is a very text-heavy card that goes into the wallets of most people. So when an emergency personnel comes to respond to them, when it becomes severe, it can be problematic just because there's too much text, and that's not necessarily something that's easy to parse. The last is basically a blood pressure monitoring system. So it's an ambulatory blood pressure system, which is cuff-based, and it goes off every 20 minutes or so. And now, if any of you had your blood pressure taken, imagine that happening every 20 minutes. It can be quite obtrusive and affects activities of daily life. So overall, these systems don't necessarily allow for a quick way to detect the onset of AD. Secondly, they tend to be cumbersome and tend to interfere with activities of daily life, causing a lot of different issues. So pressure is a singular metric, right? So only blood pressure is used in clinic right now. So wherein there's the increase of 20 millimeters or 15 millimeters of mercury systolic blood pressure change, that essentially allows them to classify that as an autonomic dysreflexic or an AD event. But it's only one parameter. We wanted to develop a non-invasive, so it's a wearable technique, as well as a multi-parametric approach that allows the detection of the onset of AD. Secondly, we wanted to automate the process by training a machine learning model that can distinguish AD from a non-AD state, but also distinguish AD from other sympathetic stressors. And I'll talk about that in just a little bit. Lastly, we wanted to optimize the performance of the model, and we did this through a combination of feature engineering techniques, which allowed us to, as I'll talk about in a little bit, I'm just giving you a quick preview of the results that are to come, of the specificity of the sympathetic activity itself. So we decided to achieve those goals through 2 specific aims. The first one was using a technique to characterize the unique signatures of AD through non-invasive sensing. And the second was to essentially distinguish AD from other sympathetic and nociceptive stressors. So primarily characterize and distinguish. So like Brad mentioned, a lot of this is based on preliminary work that I had done during my master's thesis. So a lot of that involved collecting data from individuals with spinal cord injuries through a wearable watch and using the data coming in from that watch to develop machine learning models that could discriminate between AD and non-AD events. However, the issues were that, firstly, we relied a lot on self-reported AD symptoms. So essentially, we couldn't have people take home a blood pressure monitor because of the difficulties with blood pressure monitoring overall. We didn't want it to be something that was obtrusive or came in the way of their activities of daily life. So we essentially relied entirely on having individuals who knew when their AD was happening and knew exactly how to manage it. So that way it wasn't necessarily a problematic thing that the IRB was okay with. Secondly, we couldn't control the onset of AD. So a lot of times we didn't know what the trigger for the onset of AD was. So it was very difficult to necessarily characterize specifically to one particular instance of it. So that's when we decided to do animal trials. So we investigated a bunch of novel sensors, so a variety of sensors that were used for this model. And also we characterized AD through a more controlled setting. So we were able to pinpoint one specific stimulus that was able to induce the onset of AD, allowing for a more controlled study. So with that, we'll jump into specific aim 1, which is to characterize the unique signatures of AD through non-invasive sensing. So, like I said, we wanted to use a wearable set of sensors that would be able to help us identify when AD was occurring. So the hypothesis there was that a combination of sensor data would allow us to characterize as well as detect the onset of AD. So for us to do that, we collected data from 19 male Sprague Jolly rats. These rats were between 3 to 5 months in age and weighed between 400 to 600 grams. And because we're studying the sympathetic nervous system, it's something that gets triggered whenever a stress response is generated. So in order for us to minimize any confounding effect of stress, we created an acclimation protocol where we spent 2 months acclimating the rats to the various sensors that they were going to be wearing and also to the environment that they were going to be exposed to. So it was a gradual process, an incremental process where the rats were made completely comfortable with the overall environment. After the rats had been acclimated to the setup itself, we performed a crush injury at the T2, T3 level. So this is to essentially mimic what occurs in clinic. So essentially we would have a similar representation to what we would see in the real world application in human beings. Also, crushing higher actually increases the chances of death after spinal cord injury. So we had to find a good balance between the two. And also we worked extensively with the veterinarians in Purdue to make sure that we were creating a good care protocol that can be used in future studies as well to make sure that the rats made it to the intended endpoint. And lastly, we used a well-established protocol known as colorectal distension to induce the onset of AD. So CRD essentially involves the insertion of an uninflated balloon into the rectal cavity of the animal and inflates it by 2 millimeters. So I know a lot of you are wincing right now, but the rats can't feel it because they are paralyzed below the T2, T3 level. So CRD is also a very well-established protocol to make sure that it's been done in literature several times, so we weren't recreating the wheel. So in terms of sensors, we used wearable sensors, like I said earlier. So we had skin-based electrodes, which were placed in a lead 1 configuration, as you can see on this image here. Everyone can see my mouse, I hope. But yeah. So that lead 1 configuration allows us to look at not just ECG, but also identify something known as skin nerve activity, which Dr. Everett's team has worked on extensively. The skin nerve activity allows us to measure the stellate ganglion, which is a sympathetic nerve fiber innervating the heart. So it allows us to directly measure the sympathetic nerve activity that is taking place. So that is done through a high-frequency analysis of the ECG signal itself. So in addition to the ECG and SKNA, we also looked at tail cuff blood pressure sensors. So again, this is to mimic the cuff-based sensors that we have in humans, and this was able to collect data at 2 samples per minute. And we also have a temperature sensor that was connected to this Arduino over here that allowed us to collect data twice a second. And like I said, all of the rats were acclimated to the sensor setup for 2 months prior to any sort of data collection. So here's a quick pipeline of the AD detection system. So the first step was to pre-process the data itself, right? So we cleaned the signal, we removed any potential outliers from them, and then after that, we windowed the signal. So we were able to look at differing sizes of windows and then extract features from those different window sizes itself. So we investigated time domain data, frequency domain data, and also looked at derived features. Once those features had been extracted, we fed them into 11 different classification algorithms, and we were able to evaluate the performance of each of those machine learning models. And we also looked at performing feature engineering to optimize the performance of the model so that we could look at the different ways that the features were distributed, and we were able to whittle it down to the most important features that were the most relevant to the detection of AD. So this was an iterative process where essentially we were able to tweak the machine learning models based on the features that we were getting, and that way we improved the performance to a pretty well-performing model, which I'll talk about in just a little bit. So for the signal processing, firstly, we had to filter the signal to remove any potential artifacts. So we removed any high-frequency noise components in it, so we were able to identify peaks a little more clearly. The second most important aspect of any sort of automated ECG detection system is the identification of R peaks. And we ran a Pan-Tompkins algorithm that essentially allowed us to identify the various peaks, which are the R peaks, and also the S segments that you can see at the bottom here in the circles. Once we were able to identify that, we looked at the QRS detection. So in each beat, we were able to extract the PQRST segments of the ECG signal itself. And then for SKNA related data, we were able to firstly derive it from the ECG signal. So like I said, before any processing happened to the ECG signal, we looked at the high frequency components of 500 to 1000 hertz of the ECG signal to collect SKNA data, and we cleaned it through a median filter. And like I said, the sympathetic nerve, which basically we're measuring from, innervates the heart. So the QRS interference is bound to be there. So we performed the same peak detection to remove the QRS interferences. As you can see here, this signal is devoid of QRS interferences altogether from the SKNA. The next step was to integrate the SKNA signal itself every 100 milliseconds. So we were able to come up with integrated SKNA, which allowed us to get a more intuitive understanding of the way that the skin nerve activity was performing and changing with time. Lastly, and most importantly, we looked at the number of bursts that were occurring. And so bursts essentially gives us an insight to the bursting activity of the skin nerve, of the sympathetic nerve that we were measuring. So we did this by identifying a threshold value, as you can see in this pink dotted line, and any burst was essentially values above 3 standard deviations above the mean. And so once we had done that, we also looked at blood pressure data. So like I said, we used the clinical gold standard of AD through looking at changes that happen in systolic blood pressure. So as long as there was an increase of systolic blood pressure by 15 millimeters of mercury during the CRD episode, we were actually able to detect that it was an AD event. So we had about 71% of all CRD instances actually get labeled with AD. So that was also in line with what we would see in clinic. Additionally, we looked at skin temperature, so we matched sampling rates and extracted the relevant CRD episodes from the data. So once we had done all of that, we were able to extract the relevant features. So we were able to extract 36 different features from this data itself. So as labeled here, you'll notice that the sympathetic nervous system will always be labeled in green, and the parasympathetic or the vagal activity will always be labeled in this light pink red shade. So what that shows you is really that the skin nerve activity related features are almost always sympathetic, while the ECG features can give you an insight into both the vagal as well as the parasympathetic nervous system activity. So these are pretty well-established features that have been explored in literature for several years. So we basically made use of the specific, different aspects of the literature itself. So really quick, we did a quick sanity check to make sure that the features were actually being calculated correctly. And we did this by comparing the autonomic nervous system activity before and after spinal cord injury. And as expected, there was an overall decrease in the activity in both sympathetic and vagal nervous systems after spinal cord injury, as you can see here. So the red stars are your significant features. So you can see this decrease that occurs across all of the different features that we had. So the next step was really to investigate which features were actually the most relevant. So like I said, we had 36 different features. So from those 36 different features, it's possible that all 36 are relevant, but we wanted to look on a deeper insight and get some more information about it. So the first step was to scale the features on the same range. So we did a min-max normalization to get all the features onto the same level, so on 0 to 1 scale. We also removed outliers, so we looked at the Z-score and basically removed any features that were, any data points that were more than 3 standard deviations away from the mean. We also performed a few univariate methods, so we looked at the measure of association. So we looked at doing a t-test, so hypothesis testing, and removed any values that had a p greater than 0.01. And also we did a correlation where we want uncorrelated. So we remove any features which are highly correlated. In addition, we performed a few more feature selection methodologies. The first one is a recursive feature elimination. And an RFE essentially fits a phone model with using all the features and then performs iterative elimination to end up with a subset of features that allows for the highest margin of difference between the two classes, so an RFE and non-AD. Secondly, we used chi-square testing to measure the goodness of fit. So it allows us to choose a subset of features that most closely relates to the change that's occurring in the different classes. So as shown in the table here on the right, you can see the features with the highest scores essentially are the ones which are going to be the strongest predictors for the ability to determine if it was AD or non-AD. Thirdly, we used decision trees, which are inherently able to stack up and rank the different features in their abilities to discriminate between the classes. So that was another technique that we used. And lastly, we used dynamic time warping that allows you to compare between various time series data to see how similar they are to one another. So you want to make sure that the changes that you're noticing in the physiology are actually consistent throughout your different animals. So the scores on the right here essentially show you the higher the score, the more similar the different time series data were. And lastly, we used the machine learning models. So the machine learning models were trained and evaluated using the data that we collected. And we looked at accuracy, sensitivity, specificity, and AUC-RC. The sensitivity and specificity are true positive rate and true negative rate, respectively. So, using all of that, we were able to identify 5 features from the 36 features that we collected that were able to distinguish between AD and non-AD in a clear manner. So the first feature is the median NN, which is the median value of the R to R intervals. The second is the root mean square successive differences, or RMSSD, which reflects the beat to beat variance in the heart rate and is often the primary time domain measure to estimate vagal mediated change. The third was PNN5, which is the percentage of adjacent NN intervals that differ by more than 5 milliseconds. And it's very closely related to vagal activity as well. Also, we had the average value of ISKNA, which reflects the strength of the sympathetic activity, as well as number of bursts, which look at the bursting frequency. And so as visualized through this bivariate plot, there is an ability for us to tell apart the two classes just using one feature alone. So as you can see, there is some overlap between the different classes using just one feature. But when you use 2 features, you can basically draw maybe a circle or maybe create a shape around one of the classes that allows you to discriminate between the 2 classes using 2 features. But we were able to do that with 5. So in addition to looking at those, we looked at the overall change that was occurring in the physiology just based on the sympathetic and vagal activity. As you can see here, when using 60-second windows, there is a clear, that is, there is an increase in both sympathetic as well as vagal activity. So this is also something that is expected just from the pathophysiology of AD data. Secondly, we looked at the heart rate. Look at a higher temporal resolution. So now each window represents 15 seconds of data. So as you can see here, clinically, there is expected to be a decrease that occurs in heart rate before it stabilizes after the AD episode, which is exactly what we noticed. So we see that the heart rate actually decreases, followed by an increase returning to almost baseline levels after the AD episode. What was more interesting, though, is that the cascade that occurs as a result of AD has been established in terms of the physiology, but no one has ever studied it in a quantitative manner. An interesting phenomenon that we noticed in our analysis was that during the onset of AD, we see an increase that occurs in the average value of the ISKNA and number of bursts, suggesting an increase in sympathetic activity, which occurs, followed by an increase in vagal activity, which occurs after that initial onset of sympathetic activity. So this lag that occurs in the vagal and sympathetic activity going up is actually one of a well-established sympathovagal cascade that occurs in response to the onset of AD. So this non-concomitant co-activation that we're seeing has actually not been quantified at all before in prior literature, and could potentially allow us to dig a little deeper into how we might be able to detect and identify and possibly even predict ahead of time the onset of AD. And I'll talk about that in just a little bit in terms of future work. But what I want you to take away from this slide is that you can see a clear increase occurring in sympathetic activity at the beginning, followed by a lagged vagal activity that takes place towards the end, possibly, of the onset of AD. So we decided to then take this signature that we were able to establish and then train a neural network, or like I said, 11 different classifiers. The best performing one was a 5-layer, multi-layer perceptron neural network that performed with a 93% accuracy, as well as a pretty high sensitivity and specificity. So to make sure that the model was not overtrained or overfit, we essentially used a tenfold cross-validation, and we also made sure that the data was equally distributed across all the different custom validation sets. So in addition, we also looked at the closest performing one is going to be your Gaussian process and your nearest neighbors as well, but potentially are simpler classifiers that could be used for future work if we needed lesser resources. So in conclusion, I just wanted to point out that we have used ECG and SKNA sensors to discern the onset of AD. We've characterized AD through the non-concomitant sympathovagal cascade. And thirdly, we have gotten a 93% accuracy in detecting the onset of AD. So the implications of this are that, one, this tool could potentially be used as a training or a complementary tool for individuals who are newly injured. So in addition to using that blood pressure cuff, individuals could use this ECG-SKNA combination to allow them to know when the AD is occurring and make necessarily management techniques to prevent this from becoming a more complicated instance. Secondly, that sympathetic increase is actually what triggers the increase in blood pressure, and also is what triggers all of the other symptomatic presentation. So for us to be able to identify that initial increase in sympathetic activity will provide us with a good amount of time to alert the person ahead of time and let them take the necessary management techniques to prevent AD from even occurring, or maybe even reducing the potential consequences of AD, because AD tends to have cardiovascular consequences down the line for a lot of hypertension. And lastly, we could enable alerts, which would also help people manage their AD a little better. All right. So we have shown that we can distinguish AD from non-AD, but can it actually help to distinguish AD from other sympathetic stressors? For instance, if the person is performing an exercise routine or is maybe just very stressed out at work, can we distinguish AD from those to possibly prevent false positives and also any sort of other issues that may come from false positive detection of AD? the hypothesis is yes, we can actually tell that difference. So to allow us to explore this, the first thing we did was we collected data from 15 of the male straight dog rats. So we used 3 different stimuli. So firstly, we allowed the onset of AD through the polar axial distension that we have discussed previously. Secondly, we looking at nociceptive pain after AD, after spinal cord injury, sorry. So we applied a weight of 700 grams for 1 minute on the tail of the rat to induce a pain response. And thirdly, we did a startle. Just want to make sure everyone's awake. So we essentially used a startle of 110 decibels, so a lot louder than that. So white noise for 5 seconds. So it was 5 seconds on, 10 seconds off, 5 seconds on, and so forth for a duration of 1 minute. So overall, the next step was to pipeline that data. So we looked at pre-processing, windowing, extracting those features, performing feature selection, and lastly, training our neural network. So the first thing that you'll notice across the board is that there is an increase in sympathetic activity due to all these different stimuli. So as you can see here, in blue is your neurostimulus, and you can see that there is an increase in the SKNA magnitude across all these different stimuli, but also there is a decrease in heart rate that you would expect due to AD. However, you'll notice that startle actually causes the highest increase in ISKNA as well as heart rate. And this is expected because often after a spinal cord injury, the acoustic startle reflex, which is what startle comes from, actually is a lot more exaggerated after spinal cord injury just due to the ability for neural reconstruction that occurs. However, it is interesting that AD leads to the highest bursting frequency, suggesting that the sympathetic nerves actually burst more during the onset of AD as compared to startle and tail pinch. So this is also kind of fascinating just because pain clearly would lead to more sympathetic activity, but lesser bursting that occurs in it itself. The second interesting differentiation between these different states was that during AD and startle, there is a co-activation. So like I showed in the previous chart, there was an increase in sympathetic activity that took place, but there's also an increase in vagal activity that takes place in AD and startle. However, it's interesting to note that there is vagal inhibition actually takes place in tail pinch. And like I said earlier, tail pinch is a pain response. And the body's reaction to pain is to have a parasympathetic decrease during an increase in sympathetic activity as a response to pain. So it's expected that we would see these changes take place. So can these changes actually allow us to automate it using a neural network? And the answer is yes. We were able to train a neural network to distinguish, so the same 5-layer multi-layer perceptron was able to differentiate AD from non-AD as well as tail pinch and startle with an accuracy overall of 79%. And you'll notice here from this confusion matrix itself that a lot of this poor accuracy comes from the fact that the machine learning algorithm is actually misclassifying non-stimulus data as AD and tail pinch. However, it does not do the same with the startle data itself. So a lot of the startle data, majority of it, is actually correctly classified. And similarly, tail pinch data is also correctly classified as tail pinch data itself. So all of this suggests that we have sufficient ability to discriminate between these different stimuli. So the question is, why does differentiation matter? The ability to tell apart AD from other activities, such as exercise or maybe even pain, so allows us to create a better machine learning model with poorer false positives. So what that allows us to do is prevents people from getting alert fatigue. So they don't necessarily constantly get alerts about, okay, you're experiencing AD. But allowing a better management of that enables them to also be able to know that they can rely on the device to give you correct information about when AD is actually occurring. Secondly, this could potentially be used to distinguish between different triggers of AD. So it would potentially allow us to explore whether this AD is occurring as a result of a pressure sore, or is it because of something like a urinary tract infection? So that's future work that we could use this data for. So in conclusion, AD can be distinguished from other sympathetic stressors, and we can use a neural network to differentiate between AD and other stimuli with an accuracy of 79%. So overall, in conclusion, we can say that ECG and SKMA sensors actually allow us to characterize AD on a much higher temporal resolution than has been previously explored. We were also able to perform or create a neural network that can differentiate AD from non-AD with a 93% accuracy and also have a 79% accuracy in distinguishing different stimuli. Lastly, we have developed a translation-ready tool and model that can be translated into a human version of human model of spinal cord injury to allow a better detection of the onset of AD and also potentially allow better management. So in terms of future work, we can look into the early prediction of AD. We can look into potential triggers of AD and identifying those. We can integrate other sensors to make this a more robust system. And lastly, we are looking into how we can translate this entire thing into human models, where we could actually make a difference in the lives of individuals with spinal cord injury. So here are some papers which are to be published based on this work. So a lot of these papers are almost done. So we're excited to maybe have them sent out hopefully by early next year. And lastly, I really want to thank everybody that's on this call. Dr. Duerstock, the members of my committee, thank you, Dr. Shi, Dr. Brightman, Dr. Everett, and Dr. Lin for all your guidance. Also, Dr. Walls and Dr. Bartlett played a very important role in helping us identify this. Dr. Gorgon is also not listed on there. And also everybody from the IAS and CPR labs, and everybody that has funded me, people at EPICS, and thank you to my friends and family who have been very patient with me these last 6 years. So here's an overall summary of my thesis, and I'm happy to take any questions that you may have. Thanks, Rob. I see clapping.
Yes. All right. Thank you. I'm going to open it to everyone to ask any questions.
Hi, Shruthi.
Hi, good evening.
Do you have any thoughts about how to deal with the AD that happens during, for example, exercise, when two signals triggered by different reasons kind of like overlaps?
Yes, and that's something that we're looking to possibly explore. So one of the things that we are kind of looking at overall is to be able to distinguish the different stimuli, right? So exercise triggering AD is something that occurs, and hopefully we will see the different increase in sympathetic nervous system activity initially, right? So one of the things that we could do in future work is include a lot more of these stressors in maybe a human model of this, because making rats exercise would actually induce a lot of motion artifacts into the noise as well, and make it a lot noisier. So we would have to create a more robust signal processing algorithm that would be able to tell the difference between these two. So right now the rats are restrained, so there's not a lot of motion artifact in the signal itself. But yeah, definitely something worth looking into for like future work that we have.
Okay, thanks.
Thanks for the question.
Hey, Shruthi.
Hey, Rob.
I had a couple questions about relating this to humans. So one is, for humans who experience AD, how variable is it? Is every AD in people the same? And then my second question is just the idea of using the features you identified here. How well do we understand what features would work well in humans?
Right, and those are great questions. So I'll take the second one first, right? So in terms of features that are most relevant, our hypothesis, so future work which we're going to do is to investigate how the changes in AD are to urine dynamic investigation. So essentially, we are hoping that because of the similarities in the mammalian physiology, that these features will actually translate pretty easily into the human models of it, because these are pretty well established features in both animal and human models themselves. And then, Dr. Everett, did you have something to add to that? Or okay, never mind. Okay, cool. And then in terms of your first question, which is how variable is it? So different triggers cause different sort of severities of the onset of AD, right? So a urinary tract infection may take a lot longer to clear, so the sympathetic activation may be a lot more stronger and may last for a longer duration in somebody with a urinary tract infection, as opposed to maybe a pressure sort of sore where adjusting the position of the chair may actually enable them to clear it out a lot faster. So I think future investigation could definitely look into how different triggers lead to different sort of responses. But in most commonly established protocol is that sympathovagal cascade. And we expect that just being able to identify that sort of change in temporal pattern would enable us to identify it a lot clearer. Thanks for the question.
Shruthi, this is great. I have a question in terms of like, I know this your whole pipeline is aiming for dealing with AD in spinal cord injury. Could you see your whole pipeline be applied in terms of other type of disease, disabilities and things like that?
Yeah, and I think the exciting thing about dysautonomia as a whole is that there's so many different aspects occur in different disease states, right? So it's not just spinal cord injury, but also in like Parkinson's disease or diabetes. So cardiovascular dysfunction, it's called cardiovascular, it's CAD essentially, it's cardiovascular dysautonomia, and that's like a common dysfunction that happens in people with diabetes. So it would be interesting to see how this translates out into diabetes as well as maybe even Parkinson's disease, where maybe we can identify how this affects their recovery or how it affects the way that they have dyskinesia.
Thank you.
Hey
Shruthi, this is Jackie.
Hey Jackie.
Hey, so a question I have for you kind of piggybacks on Ting's question, but I guess instead of it applying and its generalizability to other diseases, how do you think that model will translate from your mouse model to your human model? And you're using these different wearables, right, essentially, for the mouse, but how do you think that these can be applied and actually integrated into that?
Yeah, so the machine learning models, the good thing is as data comes in, it's possible to constantly tweak them. So that's one of the perks of using a neural network because of its its nature. You're able to feed it more information and it learns a little better. So in terms of the wearable sensors, actually Dr. Everett is working on a version of this with SKNA and ECG that you can make, basically allows you to pick up that data from human beings and is able, and I think you're actively using it in clinic right now, right, Dr. Everett?
Right.
Yeah, so we actually have the tools that are able to immediately translate this over. So looking at specifically SDI and looking at autonomic dysreflexia, this should be an easy translation. Shoulda, woulda, coulda, so. Thank you for the question.
Hi, Shruthi. This is Ming. That's a very nice job. Thank you.
Thanks.
I have a question in regards to the differentiator aspect of the model, in which you reported 79% accuracy in distinguishing between stimulus, but it seems to have trouble differentiating between no stimulus and AD. So can you maybe describe some future ways that you can properly hone the model and improve that type of accuracy so that we have fewer false positives?
Yeah, for sure. And I think it's kind of interesting that, you know, the idea of false positives was to reduce the false positives of AD detection, and it actually ended up like kind of, you know, working backward and making it more prominent. So I think one way to definitely tweak that would be to include more baseline data. So I think the focus of me developing the model was focused more on adding more of the stimulus data itself. So increasing the number of non-stimulus data and allowing it to characterize it a little better would be interesting. But also I think one of the issues is that in terms of the distribution of the features themselves, there is a good amount of overlap between the non-stimulus as well as the other stimuli. So maybe transforming the database and transforming the variables so that there is a clear sort of separation between the different stimuli as well as non-stimulus would be something that might be helpful in future work. Yeah. Thanks, Mike.
36 parameters, and you're trying to identify these feature sets. Were you looking at them individually or in combination as well?
So right now they're in combination, so they're equally weighted at the moment. So the other thing that we could potentially do is look at maybe changing the weight. So one of the initial aspects of my research with the human models actually involved weighting the features differently. So one of the things that we could do in the future is when we're training the network itself, we could look at the way that the weights change. So that would allow us to give priority to maybe the number of births, which it's doing right now in terms of feature ranking and all those. If we did a decision tree instead, we would see a clear way for the feature that is the most dominant to be right at the top and given the most weightage. Or like an AdaBoost based model where essentially there's more priority given to one sort of combination of features that comes up as opposed to another subset of data that we have.
So along those lines, do you have any thoughts on why some of the metrics are better than the others?
So most interestingly, we actually had a lot of time domain measures that were the most relevant, and a lot of that has to do with the fact that we're investigating 1 minute of data, right? So it's not sufficient for us to maybe create enough bins in spectral domain to actually be able to identify maybe the lower frequency aspects and the high frequency aspects of it. So one thing that we could do in the future is maybe extend the period of that 1 minute to maybe 5 minutes that we could investigate in terms of the human investigations, right? I said investigate a billion times, I apologize. But yeah, so one of the things that we could do is increase that time. So what is interesting to note is that the features are also going to be affected by the window size itself. In our case, 15 seconds seems to be the best possible resolution that we need to create enough of an understanding of these individual features. So yeah, definitely increasing the time that we can collect data from would definitely be one aspect that we could improve. Thanks, Dr. Everett.
So I have a question about your machine learning work. So I know that a lot of work must have gone into pre-processing. So I'm curious about the format of the data that you use to train a model. So you have like a bunch of different features. Was that like a single number from each feature, or you have more information?
So every 15 seconds, there's going to be an array of those 36 different features in data points. So in the final model, there was basically a 5 by 5,000, well, a 5,000 by 5, I suppose, like the rows and columns, right? So like 5,000 data points and 5 columns. So each feature got like 1 data point.
Okay, so how many trials did you need to train the model with to achieve that accuracy of 93%?
So right now we have 5,000 data points that we use and split up into the 15-15 sort of thing, but definitely increasing. And one of the best things about using a neural net is it's a lot dependent on how much data to give it. So to be able to tell apart these different aspects, we can actually provide it with more data. And that way, so right now with 5,000 data points, we have a simple multi-layer perceptron. But then potentially with a lot more data, we could even look into the deeper neural nets where we could have maybe a recursive neural net or like, convolutional layer that would allow us to create an even better performing model overall.
Yeah, thank you.
Yeah, of course, thanks.
I actually have a question. So right now was computational power and computation time a concern at all, or was that not right?
Not at the moment. And also when we are running this on the human models, I anticipate that we'll be running it on cloud. So it won't be device specific. So that way we don't necessarily have to worry too much about the resources that are going into this itself. But if we do have to worry about that down the line, that would be something that we look at maybe a nearest neighbors, right? So that's where you would create a compromise between performance and kind of computational power of the model itself. So if we can accept an 84% accuracy, you might be able to run the nearest neighbors algorithm that could distinguish between like the AD and non-AD states.
Okay, thank you.
Thank you.
So these, Shruti, all the animals were matched by weight, sex, age, and in a controlled situation.
Yes.
Yet we got higher accuracy in the humans, which were all over the place.
Mm-hmm.
What do you think?
So I think a lot of that has to do with the fact that we used a sweat sensor on the humans, right? So sweating is a very clear demarcation between a normal state and an AD state. So in these animals, rats don't sweat the way that humans do. So it's possible that the addition of the GSR sensor back into the human version of this could actually drastically improve performance, in addition to just like the SKNA and the ECG signals. So that's where I think the future work adding that extra sensor would actually be good. And also, we relied a lot on self-reporting, so it's possible that, you know, some of that may have been, I don't know, not gonna trash my previous work. You know, it's possible that some of that data may have been erroneous and it may have contributed to a better looking model as opposed to the one that we have here. But also fewer data points, right? I think that would be something, because we only had 11 subjects in that one, and I think we had about 300 data points in total that we were using for that specific study. So I think being able to have a larger database increases the variability that you would see in the data set itself.
You think that those errors, though, would trend in the positive direction in terms of being able to separate a greater accuracy, though?
I'm not necessarily sure if that, so I'm not saying it's the errors. I think it also could be that it was a simpler model, right? So it's like a support vector machine as opposed to like the neural net, which requires a lot more data. So like as we pump in more data, I anticipate that the neural network actually would perform a little higher. And I think the difference in terms of accuracy was just like 1%. Because I remember like 94 point something percent was in the human, and we have 93% right now. So it's possible that the difference may not be that drastic as well.
Do you think CRD is a good clinical model for AD? I mean, it's used well in the literature, as we know. That's why we used it. But what do you think in terms of, you know, the clinical relevance that we would see in using humans?
Yeah.
Do you think that's similar, or?
Yeah, I mean, we've written this great. So bowel and bladder distension actually tends to be the most common causes for the onset of AD, like in clinic. So for us to be able to kind of mimic that with the CRD, I think shows that there is some form or like some way for us to clinically match it with especially maybe bowel obstruction, right? That could be potentially something that leads to the onset of AD, and that's kind of what CRD mimics. So yeah, I think so. It'll be interesting to see how this performs in like actual humans though.
So Shruthi, can you rerun your human data without the GSR and compare that with it to see the change in the accuracy?
So we have actually, and so if you remove GSR from the equation, heart rate plus skin temperature actually gives you a very poor metric. So in terms of the data that we were getting, it's drastically different from this. The only similarities are going to be your skin temperature and your heart rate data. And using that combination, we actually only got like an 80-something% performance. And in fact, it was one of the poorest performing models that we built when combining just heart rate and skin temperature. So that's actually, yeah, that was like a paper that we submitted like 3 years ago.
Okay, thank you.
Yeah, thanks, man.
A silly question. So after the 2 months of acclimation, how did you know that the rats are comfortable? Did you talk to them? Did you?
Yes, I'm a rat whisperer. I speak their language. No, I kid. So we actually did measure the same metrics. So we looked at the blood pressure, we looked at the heart rate. We noticed that there was actually a decrease in systolic blood pressure, and we noticed that there was a decrease in overall heart rate. So over those 2 months, it actually trends downward. So overall, you can tell that the rats are not as stressed, even though they're like in the same environment.
Gotcha.
So not silly, don't worry.
Could you talk a little bit about the onset AD? So does that mean that after the onset, there's going to be a certain period of time before the actual symptoms happen, or?
Yes.
Okay.
So often that is the case. So in our case, we looked at within 15 seconds. So each window in this period actually is a 15-second window. So you can see that within 15 seconds, there is that increase in sympathetic activity that's occurring actually right here in this chart. So that's within one window. So within 15 seconds of the onset of AD, essentially that's when that occurs. And within a minute, your vagal activity kicks in. So that's what's causing that decrease in heart rate that we've established in the past.
Okay, so would that time period be enough for you to, to do necessary, management? It's like 15 seconds, right?
Yeah, so 15 seconds is usually not enough, but what we're expecting is a symptomatic presentation will only happen when the vagal activity kicks in, realistically. So in this case, it's like usually the moment that you perform the management technique, often it takes a little bit to have the symptoms go away, but I think Brad can speak to this as well, is that there's almost like immediate effect that occurs in terms of the symptoms kind of disappearing. So what we're able to observe is that initial sympathetic trigger that occurs, that increase in sympathetic activity, would actually precede all of the symptomatic presentation. So yes, so that should be sufficient time for the person. I mean, it's possible that the person may not even experience symptoms when the machine is detecting that they're having AD as an episode.
So can you show us what you have a predicted time frame of the rise of blood pressure? Oh, you don't have this.
Yeah, let me show. So okay, what I'm anticipating is that we'll see this increase within 15 seconds, and that blood pressure increase should occur right at window 5 or 6 over here. Window 6 or 7 over here, followed by this vagal discharge that we're expecting to see increased. So that's the anticipation, and that's kind of what Anna's on here, right? That's kind of what the hypothesis going into Anna's work is going to be, is that we will see that change in blood pressure only after we see this initial change in sympathetic activity.
Maybe they don't know Anna's work.
Yeah, Anna's, but Anna is the new master student in our lab, and she'll be taking over this project to move it forward to the next steps.
And what was using a blood pressure sensor?
They'll be using an implantable blood pressure telemetry system. So right now we're using the non-invasive cuff-based sensors, just to mimic what it would be like in human beings. But Anna's work is going to involve more implantations to get a more real-time data of blood pressure changes. So that way it allows us to compare them on a similar timescale. Yeah. All right. Any other questions?
Hi, I'm Jinxia. So I had a question for the 93% accuracy. So in your slide, you said you used 11 classifiers, and then you found the neural net gives you the best accuracy, which is 93%. So I wonder, have you compared to the accuracy from other paper, like also yours compared to theirs?
Yeah, it's a great question. This is going to sound very self-important, but the only other work that does machine learning with AD is like our work. So far there has been no other publication that works with AD machine learning related. But in terms of overall performance, so like Brad said, compared to the human work that we have, there is a slight difference in performance. But overall, 93% is a quite high performing thing. And if we were ever to submit this to the FDA, this would clear most of the bars. And Dr. Brightman could probably talk about that. But from what I know, in terms of overall performance, they expect a certain benchmark, and 93% is a pretty well-performing algorithm overall.
Thank you.
Thank you for the question, Jeff.
Okay, we have 4 o'clock. Unless there's one more question, I think we're going to ask everyone goodbye. Graduate members, any last questions? Okay.
Easy people leave. Oh, that is an annoying sound.
Is it yours? Huh?
There's something dystopian about it, like.
About people just leaving.
Why you left?
No, the internal committee will talk. You're not supposed to be there. Good, she did well.